Practice question set number 16, which prepares us for quiz number 16 tomorrow. Question 1 says a negatively charged particle is projected into a magnetic field as shown in the diagram below. Negatively charged particle enters the magnetic field. What's the direction of the magnetic force that it experiences? Some people yesterday, as you guys were working on these in class, were having a little trouble with the direction of the magnetic field. You're looking at this as saying, oh, there's a north pole and a south pole, but it's going between the magnets, so the magnetic field should go from south to north, right? No, it doesn't. It goes outside of magnets from north to the south. Just because you're in between two magnets doesn't mean that the magnetic field goes from south to north. It's only when you're inside a magnet that it goes from north to south. So here's two magnets. We have a magnetic field that leaves one north pole of one magnet, goes to the south pole of the other magnet, and a negatively charged particle that's going to the right. These guys are perpendicular to each other, right? Charged particles moving perpendicular to the field. So the hand rule that we learned is valid. We can use it. This is the hand rule for deflection. The deflection rule is what you use when you have an external field and you want to find a force. So we're going to say thumb, left thumb in the direction of the particle, which is to the right, fingers direction of the field, which is down the page, and my palm points out of the page. So my answer for this one is out of the page. B. Charged particles moving toward Earth are trapped within a field near Earth where they cause the aurora borealis and the aurora australis, which is the northern lights and the southern lights. The field in which the particles are trapped is what? Well, it's not going to be an electric field because there's no electric field to speak of surrounding the Earth. It's not going to be an induction field because, exactly. So gravitational field or a magnetic field, because both surround the Earth, right? Let's draw both of them. Here's the gravitational field surrounding the Earth. Points toward the Earth. It's not a uniform field. You can tell it's a non-uniform field here, but at any point around the Earth, whether you're at the equator or whether you're at the North Pole or the South Pole, you're going to find that the gravitational field is effectively the same. So the poles aren't really any different gravitationally than the equator is, or at least not to speak of. But the magnetic field, on the other hand, if this is the Earth, the magnetic field looks like this, surrounding the Earth. The magnetic field at the poles is dramatically different than the magnetic field at the equator. So, if you're going to get some kind of effect on charged particles at just the poles and nowhere else on the Earth, it's going to be due to the gravitational field or the magnetic field. It's got to be due to the one that's different at the poles, right, than it is everywhere else on the Earth, which is the magnetic field. So the auroras are caused by this trapping of these charged particles coming from the sun in the magnetic field, the Earth's magnetic field at the North Pole and the South Pole. So the answer for this one is C, magnetic field. Question 3. It's a great question, number 3, or numeric response number 1, I should say. It says a positively charged ion travels through a region that contains perpendicular electric and magnetic fields. So there's a positive particle moving to the right. Which way is the electric field pointing here? This is the easiest part of this question. Which way does the electric field point between a negative plate and a positive plate? Grace, which way is it going to point, down or up? It's a negatively charged plate, positively charged plate. Electric field always goes, yes, always goes away from the positive toward the negative. So there's my electric field. Now, if this is a positive particle in an electric field, it experiences a force which way? Yes, are you sure? I'm positive the force is with the field. So there's an electric force upward with the field. Well, if this is undeflected, then it's in a state of, starts with an E. It's in a state of equilibrium. And if it's in a state of equilibrium, there's got to be a couple forces that, starts with a B, balance. The electric force is up. What's going to balance it? A magnetic force that acts down. So we're going to say the magnetic force is downward here. Let's look at what the question asks us now. Match the numbers on the directions given above with the descriptions given below. The direction of the electric force. We already established that the electric force is up, so that's going to be 5. The direction of the electric field is also up. That's going to be a 5. The direction of the magnetic force is down. That's going to be a 6. Now the last question, the hardest part of it, I think. The direction of the magnetic field. What field causes a downward force? This is a deflection rule problem, right? Usually it's thumb, fingers, let's see which way my palm points. This time it's thumb, palm, let's see which way my fingers point. My thumb, my right thumb, because the positive particle goes to the right. My palm points downward because the magnetic force is downward, which means my fingers point which way? Out of the page. My magnetic field is therefore out of the page, given by the symbol 0, 5560. And number 2, numeric response number 2, or yes, I think it is. Yep, there we go. In a magnetic field with a strength of this value, an alpha particle, I'm going to circle that because we just have this temptation of using the charge and mass of an electron, since that's the most commonly used particle that we have. Travels in a circular path. What's the speed of the particle? We're going to say for this, Fc is equal to Fm. We're allowed to say Fm is equal to QVB, Fc is equal to mv squared over r. But odds are, if you've got a radius, remember what we said? If you've got a radius given to you, or you're looking for a radius, odds are you're going to do this. So let's start with that and see if it gets me what I'm looking for. mv squared over r equals QVB. One of the v's on each side cancels. I get mv over r equals q times b. Now I'm solving for v, the speed of these particles. Take the r up by multiplying, the m down by dividing. I get q times b times r over m. And when I sub the numbers in here, be careful, use the alpha particle data. You end up getting 1.72 times 10 to the 4 meters per second. This is a b times 10 to the w, so my answer is 1.72, including the decimal place. If it was an A, B, C, D question, then the answer would be 1724. That make sense? All right, and number 3. An electric field strength is perpendicular to a magnetic field strength. An electron who is perpendicular to both fields and is undeflected, key word right there, undeflected as it passes through. If it's undeflected, not going up, not going down, it's in a state of equilibrium. Equilibrium. If it's in a state of equilibrium, then the forces must balance. Good. Which two forces are going to balance here? Sometimes it's electric and gravity. Sometimes it's magnetic and gravity. Sometimes it's magnetic and electric. Which two is it here? Which two is it here? We've got an electric field and a magnetic field. It's going to be the electric force and the magnetic force. So we're going to say electric force is Q times E. This comes from the experiencer equation. E is equal to F over Q. Just rearrange that. Get F is equal to Q times E, and that's equal to QVB. Now, as it turns out here, the charge actually cancels, and I would get V is equal to E over B. So we do the math on that one, and it works out to be C 5.0 times 10 to the 6 meters per second. Is that a reasonable speed? Usually we're 10 to the 5, 10 to the 6, right? Could be lower. In the last question, you got 10 to the 4. That's a little bit lower, right? That's still fine. 10 to the 5, 10 to the 6 are the most common ones. 10 to the 7, not too bad. A and B, possible, but very unlikely because of how low they are. It's very unlikely to get a speed of a charged particle that's that low. All right? All right, let's do one more little example, application you could call it, of the same stuff that we just worked on with our practice question set number 16. This is called a cyclotron. A cyclotron accelerates charged particles to crazy high speeds. The purpose of accelerating these charged particles to crazy high speeds is to, well, simply put, Smash them together. Smash them together to see what's inside. We know that in atoms we have protons, neutrons, and electrons. Electrons are fundamental particles, but you might not know this, but protons and neutrons aren't. Protons and neutrons are made up of smaller particles called quarks. And we know this because we've investigated the composition of protons and neutrons by accelerating them to crazy high speeds and then smashing them together and seeing what comes out. So here's what happens in this cyclotron. We inject these charged particles. We'll make these ones positively charged particles. Okay, we inject a positively charged particle in the middle of these Ds here, where there's an electric field. By the way, the electric field would point this way. And it reverses up here, so that it points to the left. If I inject a positively charged particle at this point, it will accelerate with the field, because the positive particle goes with the field. It speeds up as it goes with the field, and then it leaves the electric field. It leaves the electric field and enters the magnetic field. Now, as a result of it being in a magnetic field, the charged particle goes in a circle. And you can see that here, right? Like as it leaves the electric field, it goes in a half circle. And then it speeds up a little bit more across that gap through the electric field. And then it goes in another half circle. And then it speeds up. And then it goes in another half circle. Hey, why do these half circles keep getting progressively bigger? Yeah, as they keep going faster, the centripetal force isn't big enough to keep it at that tight radius. So the radius keeps getting bigger and bigger and bigger as it keeps going faster and faster and faster, right? And that probably makes a little bit of intuitive sense. If you spin something faster in a circle, it's going to take a bigger radius, right? You take the keys on the end of this string here, swing it around a little bit like this, has a certain radius. Spin it faster, the radius goes up. Drive your car around a turn. Slowly, you can take a pretty tight turn, but if you go faster, it takes a bigger turn, right? That's exactly what's happening here. So each time it goes across this electric field region right here, it speeds up, and then it goes in a circle because of the magnetic field, goes in a bigger radius. Eventually, it gets to be a big enough radius, so fast, such a big radius, it ends up going out here and then collides with whatever we want it to collide with. We examine what comes out. Okay. Two things that I want to look at with this. One, what's the direction of the magnetic field? What magnetic field direction would cause these positively charged particles to go in a counterclockwise circle? Let's look at this, okay, using one of the hand rules. Somebody this morning, when I said, which hand rule are you going to use? Said, let's use the coil rule. This looks like a coil, doesn't it? This is not a coil rule question. Okay, let's think about why. As much as you have electrons, or protons in this case, or whatever, going around like this, which kind of looks like a coil, kind of does act like a coil, right? Right, Ryan? Kind of does act like a coil. Here's the problem. If you use the coil rule, you will find the magnetic field that's caused by the coil, not the magnetic field that causes the particles to do what they're doing. Does that make sense? The coil rule doesn't tell you why the particles do what they do. The coil rule tells you what effect that has, what magnetic field that produces. That's not what we're looking for. We're not trying to find the magnetic field caused by this charge going in a circle. We're trying to find the magnetic field that causes it to go in a circle. In order to go in a circle, it requires a force. Which hand rule are you going to use if you want to find a force? Somebody said it. Somebody whispered it. The deflection rule. Good. The deflection rule. So here's what I want to do. I'm going to say that we have a charged particle. Let's say at this point. At this point, the particle is going this way. Agree with that? At a tangent to that circle. So I'm going to use my right hand here because we said it was a positive particle. My right hand, right thumb in the direction of the particle, upwards. I don't know which way my fingers go, but I know which way my palm goes. Which way is the magnetic force acting on the particle at this point? towards the center of the circle, right? Toward the center of the circle. It's a centripetal force toward the center. So let's go right hand, thumb upwards, palm towards the center of the circle. Which way do my fingers point? The magnetic field would be into the page. Now, let's say you did it right over here. At this point, the velocity of the particle is this way. Thumb in the direction of the particle, palm towards the center of the circle, fingers point into the page. So in order to get this, my magnetic field would be into the page. So there's a little bit of a qualitative analysis of this. We don't have any numbers, so we're not going to be able to calculate anything. But let's say that you were asked to calculate the radius of the path on its final sweep. The radius of the path as it goes around here. Make sense what I'm asking? We got a charged particle in a magnetic field. What do you do to find the radius of the path when a charged particle is going in a circle in a magnetic field? This is what your practice question set was, right? Did this. Ariel, what do you do? Right. FC is equal to FM. That's what we're going to try at least. FC is equal to FM. So we'll say mv squared over r is equal to qvb. V's cancel. One of the V's cancel. R goes up, QB goes down. R is equal to mv over QB. At this point, you would probably have the mass of the particle, proton, the charge of the proton, and you probably have the strength of the magnetic field. You wouldn't know what R is. That's what you're looking for. You wouldn't know what V was either. So we have to do something else here to find V. How fast is it moving at this point right here when it starts going around in that final circle? Any ideas? There's one more thing here that you know to do. When a charged particle accelerates, speeds up through this electric field, that's like a... Finish my sentence. When a charged particle speeds up in an electric field, and that's what it's doing. Yeah, that's what it's doing, right? It speeds up every time it goes across that electric field. That's like a car going down. Yeah, red car, okay, on fire, no passengers, no driver, no insurance, going down the hill. So what do we do there? We say EI is equal to EF. Now, at the top of this hill, this car, look, this is the bottom of the hill right here. This is the top of the hill right here before it goes across that gap. At the top of the hill, is it moving? Is it moving just before it goes across that gap? Absolutely it is. So it's got kinetic energy at the top of this hill. It's also got potential energy, except the potential energy is QV, not MGH. Now, at the bottom of the hill, it's got kinetic energy. What you would do here is solve for the final speed at the bottom of the hill or after it's gone across the gap, sub that value in here, and then solve for R. Does that make sense? Tell me, if this was a numerical response question, and it could very well be, you will get question, most likely 49 and 50 on the test. They tell us we're going to get one of these questions, not necessarily this topic, but a question that's like this. And they don't tell us where it's going to be on the exam, but usually it appears as the last two questions, 49 and 50. They give us this question. They ask us to solve for the radius. You've got it. Perfect. You solve for it. Done. And then you read the next question, and it says, which two physics principles did you use to solve this? Take a look at the back wall or take a look at your data sheet to look at the physics principles. Which two physics principles did you use in order to solve this? Forget about the order right now. Just tell me which two you used to solve this. 2 and 5. Yeah, it's 2 and 5. Okay, 2 is uniform circular motion, and 5 is conservation of energy. So what do I list it? 2 and 5? Or do I list it? One of these days I'll get this right. Is it 2, 5, or is it 5, 2? Which order did we do it? Well, we kind of did it 2, 5, And then we came back to 2. What do we put here? Here's what I want you to do when you see this question on your exam. Not this question per se, but you know what I mean, this type of question where you have to identify the physics principles. Identify the one you did last. What got you the answer? This got you the answer. So list that last. Don't worry about which one you did first. Worry about which one you did last. What got you the answer? List it second. And then the other one, you're going to list first. So the answer to this 2 physics principles you used would be 5, 2. Does that make sense? Now, we've talked a little bit about written response tests. Okay, after the break, about a week after the break, you're going to have a momentum written response test. Okay, just before the break, I'll give you a handout with some questions on it that'll provide you with a nice little review of all those topics within momentum so that you can feel comfortable with going into that written response test. About a week after that, you're going to have an electricity/magnetism written response test. Okay, we're going to combine those two, electricity and magnetism. Now, I've got to somehow come up with a question that involves both electricity and magnetism for that written response test a couple of weeks after Easter break. Those are hard to do. It's hard to find questions that involve both electricity and magnetism in the same question for your test.